Welcome to the Ontario High School video podcast. We're doing a Hess's Law series here in chemistry. We're on part 3, which those of you who've listened to part 1A, part 1B, and part 2 will know part 3 actually is part 4, but we're going to keep that secret between us. We're calculating heats of reaction through the examination of a series of related reactions, and we're going to look at an efficient alternative to the very long way that we've been doing these problems. So here is the efficient alternative. One of our mottos in AP Chemistry is that the long way is never the wrong way. And I've shown you up to this point very long ways of doing Hess's Law type problems. Here is a shorter way, but you really have to understand the long way before this will make sense to you. If you don't think you understand the long way, go back and watch parts 1A, 1B, and part 2 before you watch this one. Okay, the efficient alternative is this. We know that the overall change in enthalpy for reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpy of formation for the reactants. The sum of the enthalpy of formation for the products is the sum of the enthalpy of formations for each of the products. You add them together. The sum of the enthalpy of formation for the reactants is the sum of the enthalpy of formations for each of the reactants added together. The information where you can find what the heat of formation for compounds, these are found in the appendix of your text. If you have an obscure compound that isn't listed in your text, you can always use an efficient internet search engine to find information on that. It's widely available. Let's look at a reaction. Those of you who know Spanish will think this is quite an ugly reaction, but we have iron 2 oxide solid being reacted with carbon monoxide gas, and what that does is it liberates the iron and removes the oxygen from it so that the iron can be used. So we get elemental iron plus carbon dioxide gas. Now we're going to use the enthalpies of formation for the relevant compounds to solve for the enthalpy of reaction for the reaction as it's written above. So we have a table, iron 2 oxide, FeO, the delta H of formation for that is negative 272 kilojoules per mole. For carbon monoxide is negative 110.5 kilojoules per mole, and for CO2 is negative 393.5 kilojoules per mole. You'll notice there is not an enthalpy of formation for elemental iron because any free element always has an enthalpy of formation of 0. Well, using these table of these enthalpies of formation, we can certainly calculate what the sum of the enthalpy of formation for the products is. For carbon dioxide, it's negative 393.5 kilojoules, and we're going to add that to the 0 kilojoules related to the iron. For the reactants, the formation of carbon monoxide is negative 110.5 kilojoules, and we're going to add that to that of iron 2 oxide, which is negative 272 kilojoules. So the sum of each of those, the sum of the enthalpy of formation for the products is negative 393.5 kilojoules. The sum of the enthalpy of formations for the reactants is negative 382 kilojoules. Let's look at this. We need to make a change first of all. On the left-hand side of the equal sign in each of these equations, you have the summa symbol delta HF with the 0 that represents standard conditions. We need to change those. Would you eliminate the summa symbol? What should be on the left side of the equal sign is delta H RxN, that we're looking for the enthalpy of reaction here. So I apologize for slipping in the wrong symbols here, and if you would change those to delta H reaction, eliminate the summa sign, and replace F with RxN, and we'll be okay. We're going to find the heat of reaction by subtracting the sum of the enthalpy of formation of the reactants from the sum of the enthalpy of formation of the products. And when we do that, we get negative 393.5 kilojoules minus negative 382 kilojoules, and that will give us a total of negative 11.5 kilojoules as the heat of reaction. So that's how this problem is done. Again, watch your symbols, and we'll take care of this. Well, here's a problem for you to try. Here we have the combustion of propane. C3H8 plus 5O2 will yield 3CO2 plus 4H2O. I'd like you to calculate the heat of combustion of propane using the information from the table below, which gives you the enthalpy of formations for each of the compounds. Again, notice there is no enthalpy of formation for the O2 because any free element has an enthalpy of formation of 0. So if you will pause the podcast and go ahead and complete this problem, and when you want to check to see how you did, go ahead and resume the podcast and we'll compare notes. Thanks. Welcome back. Let's see how you did. Now, one of the things that you have to do with the information in the table is if there are coefficients greater than 1, then you need to multiply the delta H of formation, the enthalpies of formations, by those coefficients. So when we find the sum of the enthalpy of formation for the products, we have to multiply 3 times the enthalpy of formation of CO2, which is 3 times negative 393.5 kilojoules, plus 4 times negative 285.8 kilojoules, which is the enthalpy of formation of water. When we do that, we get negative 1180.5 kilojoules for the carbon dioxide, plus negative 1143.2 kilojoules for the enthalpy of formation for 4 moles of water. And our final value, the sum of the enthalpy of formation of the products, is negative 2,323.7 kilojoules, or negative 23.7 kilojoules. We also need to find the sum of the enthalpies of the reactants. Very happily, the enthalpy for oxygen is 0, and that makes that real easy to add. For the C3H8, it is negative 104 kilojoules. So we just add negative 104 kilojoules plus 0 kilojoules to give us the sum of the enthalpy of formation for the reactants as negative 104 kilojoules. On the left-hand side of the equal sign in both these equations on this slide, would you just scratch out on your paper, not on the screen obviously, but scratch out the Greek summa symbol. All we really want is the heat of reaction is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation for the reactants. So the sum of the enthalpy of formation for the products is negative 2323.7 kilojoules, and then we take that minus negative 104 kilojoules, and that gives us an overall change in enthalpy of the reaction as negative 2219.7 kilojoules. So our heat of reaction for this reaction was negative 2219.7 kilojoules. How'd you do? If for some reason you did not get this answer, would you go back to the beginning of the podcast, kind of set these notes aside, rewatch the podcast, and try this problem again and see if you can get the correct answer on your second try. And if you can, it will be well worth your while. Well, we're at the end of the Part 3 broadcast, which is really the Part 4 video podcast regarding Hess's Law. You now know more about Hess's Law, perhaps, than you've ever known. You certainly know more about my fallibility, and that's no big deal. But we're at the end. I want to leave you with a quote again by the eminent playwright Eugene O'Neill. "A man's work is in danger of deteriorating when he thinks he has found the one best formula for doing it. If he thinks that, he is likely to feel that all he needs is merely to go on repeating himself. So long as a person is searching for better ways of doing his work, he is fairly safe." I wish you well.